Hello everyone, welcome to Physics CQ-METANS. This is the fifth video lecture on vector analysis. These are the topics we will be discussing in this video. I will start with differentiation of vectors and discuss about the fields. Scalar and vector field we will discuss. So these fields are very important. We will see why it is. Next is differentiation of vectors. So if we have a vector A, which can be written as Ax I cap, Ay j cap plus Az k cap, where I, J and K are the fixed unit vectors. Remember, I am using the word fixed, so they are fixed. While this Ax, Ay, Az are function of some time, then we can define a derivative. So we can take a derivative of this vector A with respect to time, and we can write dA by dt as this. So we are just differentiating the coefficients over here. So we have written here the derivative of a vector A means a vector whose components are the derivatives. So we are just derivating the components. Now let us take one example. Now let us say we have a coordinate system, the x, y and z coordinate system, the Cartesian, and there is a point over here x, y, z. So now we have a particle, a moving particle. So say this is the particle which is moving with time. So the coordinates of this particle is changes with respect to time. So this x, y, z are time dependent. So they are the function of time. So this is the particle at this point. So at a later point, this particle might be over here. So the position of this, the coordinates of this particle changes with time. So x, y, z are the function of time. So we are defining a displacement vector r. So remember, when we discussed about the line, we said r is equals to x minus x naught plus y minus y naught j cap plus z minus z naught. So same way we are doing over here, but only the thing is the x naught, y naught, z naught in this case is 0. So the displacement vector is given by this r is equal to x I cap plus y j cap plus z k cap. Now if we differentiate with this displacement with respect to time, we get the velocity vector with the components dx by dt along x direction, dy by dt along the y direction, and dz by dt along z direction. So the velocity vector is given by this. Now if we further differentiate this, we will get the acceleration. So acceleration will be, so d is missing over here, sorry. So it is acceleration is equal to dv by dt. So if we just differentiate this, we get d2x by dt square I cap plus d2y divided by dt square j cap, and so on and so forth. Now when we have dealt with the vector, we know that we have the cross product and the dot product. So how to find out there are certain things when we talk about the differentiation of them. First, we will talk about a scalar, the product of a scalar. So this E over here is a scalar. So this, we have a scalar quantity over here. So product of a scalar and a vector. So and the dot product and cross product can be differentiated by ordinary rules of the differentiation. So if we know that, like if I have a differentiation of two quantities, I can take one constant, differentiate other. Same thing we are applying over here. So d by dt of a scalar multiplied by vector. So I will differentiate the vector, keep the I will differentiate the scalar keeping the vector constant, plus the scalar keeping constant, I will differentiate the vector. But something happens, something should be noted over here. So A dot B, we know it is commutative. So A dot B, I can write it as B dot A because they follow the commutative property. So if I differentiate this, so if I write dA by dt dotted with B, this is fine. Otherwise, if I write B dA by dt, that is also fine. So over here we are writing A dB by dt plus dA by dt. If I would have written in the other way, like dB by dt dot A, that would also be fine because it it obeys the commutation relation. Now next is cross product. Here we have to take some caution because we have seen that A cross B vector is not equal to B cross A, but rather it pulls a negative sign. So we have to take the care of this. So when we are differentiating, so if I am applying, so if I am differentiating this A, keeping B constant, so I should write dA by dt, and see, the order should not be missed. So if I am substituting this inside, so if I differentiating the first one, so the second one should be at its place. We cannot move it. We cannot say that B cross dA by dt, so that is wrong. So this ordering should be maintained over here. So this is the derivative. Now we will see one example, a very nice example in polar coordinates. Suppose if I have a particle in polar coordinates, so what we will have? So the polar coordinates is represented by r and theta. So if we have this coordinate system, so if we have this x and y, this is the vector. So this position of this vector r. So this point can be defined as r comma theta. And this vector is at some angle theta. So now if we are moving along the line where theta is constant, so we are moving along this radiator. So we are moving in this direction. So if we do so, if we are moving in the direction of r, increasing direction of r, we call it as r direction. So there should be an unit vector. So if we are moving along r in the direction of r, so there is an associated unit vector which we will name it as r cap, or in the textbook you will find it as er cap. In the same way, now suppose if we are moving on a circular path, suppose if we are moving on a circle, so in this case the radius is same. Now what happens is, so let's say the radius is u. Now at this point the angle is theta. Still the radius vector r is equal to 1. Now if we move over here, the angle changes. So if we are moving with constant r but in the direction increasing to theta, now how the theta increases? Tangentially. So in the increasing theta, we call it as theta direction. And what should be the direction? So direction is the vector that is tangent to the circle, and it is represented as theta cap. So this is the direction of theta. So we have two unit vectors. We have defined two unit vectors. One is r cap and one is theta cap. R cap is the unit vector which is along the direction of radial vector, that is r, and theta cap is the unit vector which is tangential or perpendicular to this r. So these are similar as just as we represent in the Cartesian coordinates I and j, they are similar to them. Now, so what we can do is we can write any vector in terms of r and theta. So if we write so, then there is one thing we should be taking care of. So in the Cartesian coordinates, I and G are fixed, which means that their magnitude and direction is fixed. It has a constant magnitude and direction. So if you notice, we have this coordinate system. This is x, this is y. So the unit vector along x is I cap and here j cap. So this unit vectors are fixed. They are not going to change. But polar coordinate is not the case. The basis vector changes. The magnitude remains the same, but the direction changes from point to point. Now, if we just see in this part, so this was the radial direction. Now, suppose if I take another, say if my particle is moving and the particle goes away. So this will be the radial vector now. Will be the direction of radial vector. It is in this direction. So if you notice the radial vector, unit vector, this basis vector r cap does change. So if the position of the particle, so from it changes at each point. Similarly, if we see theta, so over here and this, when the particle was here, direction, the direction of this theta cap was tangent in this way. Now, when we move over here, the direction of theta cap is like this. If we move up the particle over here, the theta cap will be in this direction. So if you notice r and theta, r cap and theta cap changes with, so they change from point to point. So we have written, so the polar coordinate unit basis vectors, that is r cap and theta cap, are constant in magnitude, but that direction change from point to point. So now while taking the derivative, we have to take care because this r and theta have become a function of time. So this r, now at a certain point, of time, this is the position of the particle. At a later point, this becomes the position of the particle. So r cap changes. So r is a function of time. Similarly, theta, for theta, this was the theta at some time. Later it changed. So theta cap is also functioning. So while calculating the derivative, we have to take care of this. So we should differentiate the basis vector as well as the components. So now this is the coordinate system. Now let us see how can we deal with that problem. We don't have to differentiate this dr, r cap and theta cap. It is very complicated. So is there any way out? So there is one way to express this r cap and theta cap in polar coordinates, unit vectors, that is I and j. So this is x coordinate and this is our y coordinate. So now this is our vector. This yellow color line is the vector r. Now in the direction of r we have r cap. So this one is r cap, and perpendicular to it, or the tangential direction of to r is theta cap. Now if I just translate this coordinate x and y, suppose I'm again repeating this, if I have a vector, and suppose if I have kept a pin over here, and if I just displace this pin and take it over here, so is it change? Is there any change? The answer is no. The direction and the magnitude, the length of the pen is same, and the direction what it was pointing is also same. So the even if I change the position, the vector remains same. So this is called as translation. So if I translate this coordinate from this point to this point, taking the coordinates to be 1, so this becomes I cap and this is j cap. So now this vector r is at some angle theta from x axis. So if this is the angle theta, then this will be also the angle theta, because this I and this x coordinate, these are two parallel lines and this is the transversal. So if this is theta, then this should be theta, corresponding angles. So if this is theta, then this also should be theta. So now how can I write? So r cap, if I take a projection, if I extend this, sorry, so if I take the projection, so r will be equal to, so unit vector, it is unit, so the magnitude is 1, so it will be cos theta I cap plus, now we will take the projection over here on the y-axis. So if we take, we get sin theta, so this becomes j cap sin theta. So in the same way, if I take the projection of theta cap on the x and the y-axis, so if we extend this as well, so we will get the projections. So theta cap will be equal to cos theta cap plus, sorry, minus sign, because it is in the negative x-axis, so it is minus I cap sine of theta. So this r cap and theta cap we get. So as mentioned, r cap is I cos theta plus j sin theta, and theta cap is minus I sin theta j cos theta. Now we differentiate this. So dr by dt. Now if we notice, we have transformed our coordinate in I and j basis vector. So now differentiating r. So if I differentiate this, so if I do dr by dt, so I will get, so I cap. Now I cap is fixed, so I don't have to bother about it. I don't have to differentiate it. So only cos theta. Differentiation of cos theta is minus sin theta, which came over here, and differentiation of theta with respect to time is d theta by dt. Similarly, if I do sin theta, differentiation of sin theta is cosine of theta, and this theta dependence on time comes over here. Now if we just write this, I will show it over here. It is dr cap by dt, that is equal to, if I take d theta common, d theta by dt we take common, so what we get is minus I sin theta plus j cosine of theta. is this bracket term, it is nothing but theta cap. So we can write it as theta cap d theta by dt. In the same way, if we do for d theta dt, so we get this if we differentiate this one. So sine theta is cosine theta, so it comes over here. So if we simplify this, we will get the answer as minus r cap d theta by dt. Just write. Now we move on to the next very important topic, that is fields. Now why there is a concept of field. Now if we consider physical quantities, they have different values at different points. So if I take a xyz coordinate system, and suppose if I drop an ball or something, so at different point its value will be different. Or say I do a projectile motion, I am throwing a ball like this, so at different point the velocities will be different. At maximum height the velocity will become 0, so on and so forth. So the physical quantities have different values. So what we define the field as, so field is a physical quantity, so it is represented by a scalar, vector and a tensor, so that has a value at each point in space and time. So now if the physical quantity, if we are talking about physical quantity which is a vector, so it is a vector field. And if the physical quantity is a scalar, then the field is a scalar field. So if we are talking about a physical quantity which is scalar in nature, then we are talking about a scalar field, vice versa. Let us discuss about the scalar field. Now in order to understand scalar field, let us consider temperature, a scalar quantity, that is temperature. Now if I just sit in a room, so if I am near the gas stove, so I will feel the temperature is high. While if I go to the nearby open window, so the temperature over there will be less. So this difference in temperature. Now when I am standing in front of stove, there is a field. So what field? High temperature. If I go to the open window, next to the open window, the temperature field is a temperature field of somewhat low temperature. Another example of a scalar field is gravitational potential energy. We know that the potential energy is given by mgz, where z is the height, from some arbitrary reference. Now we consider an example of an hill. So say this is the hill. Now we make some curves. We mark some series of curves over here. Now each curve or each line will represent a constant potential, because if we see this curve is at some height z, this curve is at some height z, so all the points on this curve, all the points sorry all the points on the curve will have the same potential. So this line is called as equipotential. So we have written over here, suppose we have a hill and we mark a series of curve, so each corresponding to some value of z. So any curve on which a potential is constant is called as equipotential. So this line, these are called as level lines, are equipotentials of gravitational field. Now suppose if we take a horizontal plane, so if we cut this part, for instance, we will see that there is a plane over here, or if we cut this part we will see a plane over here. So what this plane represents? This plane which intersects this curve, the horizontal planes which intersect these curves are called as equipotential surfaces. Equipotential surfaces are important in the electrodynamics when we will study potential. Now we move on to the vector field. Now, rather than giving some definition, let us see how a vector field will look like. This is an visualization of vector field. Now consider this vector, that is 2x I cap minus y I cap. So let us take our coordinate system. So this is x, this is y coordinate. Now let us plot couple of points. So let's say x is equal to 0 and y is equal to 0. If I put this value x and y in this A, we will get this A as equal to, so vector A is a 0 vector. So this is the point, this is the origin. Let us take more point. Now let us consider a point where x is equal to 1 and y is equal to, so this point corresponds, so we are putting this one, so it becomes a to j cap. So the a is equal to 2 cap. So we say that this is 1, this is 2, this is 3, and so forth. So what this means, x is equal to 1. So at 1, y is equal to 0. So this vector is pointing like this, which has a magnitude of 2 units along the j cap direction. Now if I put x is equal to 0, if I take x as 0 and sorry y as equal to 1, so what we are going to get, so if we put this in this equation, we will get y a as equal to minus a as equal to minus I cap. So which means that at y is equal to 1, say this is 1, 2, and so it is a negative y. So there is an unit vector minus I cap, and it is like this. So this is the vector. It has the magnitude 1 unit. So if I put x equal to 1 and y also equal to 1, so what we get? We get this vector as is equal to 2 j cap minus I cap. Now if I plot this, so 1 1, so this is 1 1, see this point is 1 1, so minus, so it is 2 j cap. 2 j cap means 2 in the 2 units along axis and 1 unit along the negative x. So the resultant of this vector will be like this. So if we plot all these points, if we go on plotting, we will get this kind of graph, a very beautiful graph. So it represents the curling effect. This vector, we will, when we solve this vectors, when we will study the curl and all, So we will see that this kind of field represents something called as curling. So suppose just for example, if I put a, if I put one, say, some paper over here. Say I cut a strip of paper and I place it over here. Now what happens is, and say this is a force field. So if you see, the magnetic force is more over. So what is going to happen? This downward is like this, and or else we could have taken it this way. And if I apply, this one is applying a force upward, so this paper will turn to rotate. So this is called as something rotational field, or the rotational, the curling effect. We'll see, we'll study curl. That is why this curl, this vector and the scalar field is very important. Now this is a vector field. This is drawn in the 3 dimension, so it is a bit difficult to visualize. We will see the same field when we will study some positive charge in electromagnetism. Now this one field which we like to see, so the vector is 2x I cap plus 3y j cap. Now if we plot this, so you will find all these vectors are pointing away from some point. So there is a point at the center, say somewhere over here maybe, and these vectors, they are pointing away. So they are moving away from a point. Such a field is called as diverging field. Diverging vector field. So from a single point, the vector we will see. So we will draw more graphs. We can see that this will have more magnitude at this point, and as they go away, the magnitude increases. That is what an electric field is. So if I have a positive, so if I keep a positive charge over here, so this is how the electric field will look like. But only the thing is that the magnitude increases as we go away from the, here it is the magnitude increasing as we go away, but that first case will be if I keep positive charge over here. Now something more we have. Now suppose if I take this, now you will find that all the vectors, so all this vectors of this A for different x and y values, they are pointing towards one point. So if I put the values of x and y and draw this graph, so they will point at a certain single point. So it seems that all the vectors are coming to a single point. So such a field is called as the converging vector field. So it is also referred to like positive divergence and negative divergence. So we will see. So the next topic will be of this directional derivative and gradient, and later on we will discuss about divergence. At that time you will understand what is the importance of this converging and diverging fields. We will have something called as the negative divergence, positive divergence. So there we will again see this concept of converging and diverging vector field. So I hope you understood everything well. I hope you are finding this videos helpful. So thank you all. Thank you all for joining me. So see you all in the next video. Thank you.